I'm Kary Rogers, Director of Tech Support Americas West at Riverbed. I started there, 10 years ago answering phones, maybe talking to you, maybe talking to people you know, helping them solve their steelhead optimization problems. And I found that the better I was at looking at packets to understand what was happening on the wire, the quicker I could solve problems. So at every chance I could, I would use Wireshark, I would get packet captures, and I got better at doing it, I got faster at solving problems. And a few years ago, I went to the dark side in management, so immediately all the technical knowledge I had went overnight out of my head. But before the packet analysis completely drained out, I dumped some of it on the internet. It's a little website called packetbomb.com. So what we have today, I think so anytime you have questions, just shout it out. I'll probably be looking down at the screen. I may not see a hand, so just shout out if you have a question. We will be doing some case studies. Has anyone, this is the first time to see case studies from me? New people? All right, I think a good number of people. These case studies I did do in Europe last year. Just an FYI, and these are problems that people reach out to me over email or whatever and say, hey, I have a problem, can you help? And so these are real folks. We'll get into a little bit about that. So what I call the packet A team, packet analysis team, where people sometimes I find them on Reddit, sometimes they post a problem, and I'll say, give me a PCAP, we'll try to figure it out, or they just email me. So that's where these case studies come from, and I think that's enough to know up top. I'll be giving you, a very brief overview. The slides are not really much here, just a quick overview of the problem, and we'll dive into the PCAP, and then I'll give you some takeaways that I think are takeaways, but really you should have your own. Maybe some things some things are new to you. Whatever those are, I don't know. But make sure you have your own takeaways from this. And with that, where's my...
Thousands of people turn to the internet for help because they have a burning computer and network problem that they cannot solve. If you have a problem, if no one else can help, and if you can find them, maybe you can hire the Packet A team.
All right. I guess everyone knows and loves the A team from the 80s. If not, you're like, what in the world are you? That's just my little fun thing to do. So before we get started, I generally have a very similar approach when I get sent a PCAP from a stranger on the internet. Some things that I look at, how I want my Wireshark to look. So let's just run through a few of those before we get into it. Things I've learned on my own, tons of stuff I've learned here at SharkFest. I think I'm wearing the first SharkFest I ever went to t-shirt. I actually found it this week, buried in a bag somewhere in a closet. I was like, hey, great, I'll put it on. I've learned from tons of people here, and so my process is sort of take what works for me, things I've learned, and put it all together. So that's what you're doing. You come here, you listen to people, you're looking at packets yourself, you're watching YouTube videos, reading books, all that sort of goes into your brain, and you'll have your own process, but let me talk about mine. So if you're going to add one thing to Wireshark, I would add a delta column. To find the delays, how many times you're looking for performance issues, things that are broken. A lot of time, big delays, big delta, time between packets. You can sort on it, you can highlight it, you can do whatever you want. I would say add that in there. Then when I get the PCAP, I like to go look at the conversations. They just tell me, hey, it's a web problem. Hey, it's an NFS problem. We're doing iPerf. Okay, well, I wasn't there. I don't know how you captured. I don't know what's in this thing. So I like to see, am I looking at, is there one TCP connection in here, or are there 1,000? Just to kind of get the lay of the land. Three-way handshake is so important when you're capturing data. There is information in there that you can't get anywhere else. It's only presented in the three-way handshake. So if you don't get the three-way handshake, you're going to miss some important bits of information, and we're going to go through that through the case studies. And then I think it's if you're doing this day in and day out, I no longer do it for my day job. I do it occasionally, for strangers on the internet. But if you're looking at PCAPs all the time in different scenarios, different protocols, I would suggest you start from like a base, and then as you make changes, you can save those profiles. You can save one as HTTP, SMB, TCP, minimal if you want minimal columns. And then you can switch back and forth as needed. For myself, I usually just kind of have one base one and there's only a few different columns I'm probably going to put up as I go through. So that's how I start out. That's how I approach. Let's jump into the first one. And I'm not sure, I think I have done this one at some SharkFest in the past. If it's not new to you, it'll be a good refresher. This one I think is really interesting. So this person emailed me. They had a new data center connected to AWS with 1 gig, and of course, hey, we have something new, and we're not getting the expected performance, right? I mean, you've probably run into that before. We all assume it's the network. Well, we don't, but people do. So he's had a PCAP. He said, hey, we did an iPerf test. That's something that people do a lot to try to determine, am I getting the bandwidth that I expect, that I'm paying for, etc. I would say most times that people come to me or post on the internet about, iPerf, I'm only getting 2 megabits when I should be getting, 50. They probably haven't set up the test very well. They're not using the iPerf config, giving it the proper window size, etc. And you can see that in the PCAP. So I expected to see that in this. And let's jump in straight to the PCAP, and we'll have a see if we can figure out what the throughput issue is. Is that good enough? Should it be bigger? Can you see okay? A little bit more? All right, we can do that. Better? I know there's a lot of, there's a lot of other things assaulting your eyes right now with my layout, and I'll walk you through some of this. Again, if anything needs to be bigger, smaller, explained, just let me know. Let's make this smaller. So this PCAP, okay, you give me a PCAP, what's in it? I go to Statistics and Conversations, and I see, I think you can see that, two connections. One with just 28 packets, one with a lot more. So that's probably the one we care about. I see, when you go through PCAPs, things will kind of jump out at you, just kind of, maybe it means something, maybe it doesn't. I see port 1025, that means something to me. Does it mean something to you? Is there anything special about 1025? Well, it's one more than 1024, right? What's special about 1024 and under, right? It is, and you have to be a super user root, whatever, to bind to ports under 1024. So, okay, does that matter? Probably not. But again, the more you look at PCAPs, the more things, and the more you read RFCs, documentation, things, these little puzzle pieces just kind of float up, you file them away. Maybe they come back up, maybe they don't, but you learn to notice things. So then I want to know, do we have the three-way handshake? Whoa. Yes, we do. SYN, SYNAC, ACK. Another reason why it's important to get the three-way handshake, because you can look and you can make a determination, usually, get a good idea of where in end-to-end you captured this data. It says, you probably can't read it, but the name of the file is receiving, okay. But in terms of, are we on the client side, are we on the server side? With the three-way handshake, you can many times kind of figure out at least the ballpark of where you're at. So if you think about, if I'm initiating a connection to a server and I'm capturing, that SYN goes out at time 0, right? It travels across the connection, the WAN, whatever it is, to the server. The server immediately sends a SYN ACK back to me, and that's one round trip. And then I immediately ACK. So the delay is between the SYN and the SYN ACK, right? The delta. And if I'm the client. If I'm the server, you switch it, right? I'm sitting there minding my own business. When a SYN shows up out of nowhere at time 0, I immediately send a SYN ACK back. The SYN ACK has to go back to the client, which then responds with an ACK to complete the Threeway handshake. There's the round trip between the SYN ACK and the ACK. So which side, in terms of client and server, would you say this is captured on? And my delta column is here. Yeah, the server side. It's between the SYN ACK and the ACK. So, what do we have? We'll make this a little bigger now. I usually like to just take a quick gander at the options to see what's there. MSS, SAC, timestamps, no-op, window scale. Okay. Nothing really jumps out at me, but it's good to see. Something red shows up here when I click on the SYN ACK. Maybe I want to know what that is. Header checksum. Header checksums sometimes are, if you capture on the host, they're not correct because of offloading to the card. The card itself might do the offloading, or might do the checksum calculation and stick it into the packet before it goes out on the wire, but you're not capturing. If you're capturing on the host, you're capturing before the packet gets handed to the NIC. So we can probably ignore that. Maximum segment size, no op, window scale, SAC, timestamps. Okay. Anything different here between the two? Window scale? Yeah, good to know. They're a different order. Is that a problem? No. You'll probably hear me say a lot, is that a problem? Because sometimes it is, sometimes it's not, sometimes you don't know. So we have two connections, one very small, and if you look at iPerf traces enough, you start to see some patterns. iPerf 2 generally has one connection. At the very beginning, after Threeway handshake, it'll exchange like 24 byte packets before the data flow starts. In iPerf 3, I've seen more of an FTP behavior of like a control channel and then a data channel, and that appears to be what's happening here. So if I had to guess, I would say it's iPerf 3. We go down to the second one, just to do a quick check. It looks the same, SYN, SYNAC, with our options and our round trip time around 9 milliseconds. So, with this, why don't we just kind of scroll through here, and just a quick word about, again, my layout. I know it's a lot of numbers. I like to have the sequence number information in my columns because a lot of these things require you to follow the sequence numbers, right? What are the order you expect this to be in? Is this a real retransmission? Is it not? So I like to have that there. If you're just starting out and it's overwhelming, you can take those out and look at them as needed. So let's move just a touch. We'll take a scroll down here, just kind of eyeballing it. And you can pretty quickly see a pattern, right? So this is bytes in flight, this 1448, 2896. So this is data being sent, right? 1448 bytes. This is the TCP length. And I don't know if you can see my mouse where I guess maybe. Over here on the left. So we're sending 2 packets and an ACK. 2 packets and an ACK. And that's pretty standard TCP behavior. data, data, ACK, data, data, ACK. And the bytes in flight never get above the 2 packets because we're on the receiving end. We're receiving this data, so as soon as we get the 2 packets, we ACK. As soon as the 2 packets come in, we ACK. So that's the pattern that we see. Now, once I get the lay of the land, I kind of see what we're dealing with, and I'm looking at throughput, my go-to tool is under Statistics, TCP Stream Graph, and TCP Trace. Let's make this bigger, and then we'll walk through this. So I like pictures. I'm a visual person. I learn, I think, better visually. So what this is, the x-axis is time in seconds, and the y-axis is sequence number. And sequence number in TCP is just a representation of bytes, right? That's how we keep track of where we are in the flow of data. So one sequence number is 1 byte. So I have relative sequence numbers turned on, meaning that at the beginning of a TCP connection in Wireshark, it starts at 0. When the real number is going to be a randomized 32-bit integer, but we're starting at 0, so relative sequence numbers. So what we want to see is this line, this throughput line, going up and to the right. So more bytes are being sent over time, right? This is sequence number over time, which is bytes over time, and that's throughput. So let's zoom in so we can see a little better of what we're dealing with and talk a little bit more about what this is. So these little guys are the packets. The length along the XY axis is how big the packet is. So if it's a real long one or a real short one, just at a glance, you can see how big that packet was. The line below it are the ACKs. So remember, if we're going to the right, this way, that's time moving forward, and going up is more data being sent. So right here where the mouse is, we sent 2 packets, and the green line goes up just very shortly after, just probably microseconds after, and now they're at the same level, meaning this data has been ACKed. We get 2 more packets, and then the ACK line goes up, meaning that those packets have been acknowledged. Okay, so that's data being sent and the acknowledgements for them. And then after that, there's a flat line where nothing is happening. So that at the beginning of this connection, which is where we are, you can see there's a little bit of data, and we wait, a little bit more data, and we wait, and the amount of data we're sending each time is increasing. So in TCP, what is that usually? Slow start, the beginning of a connection. The other line up here is the receive window. So if we're down here, the space between the packet and the receive window is how much space is in the receive buffer. So that's the receiver saying, in every packet it sends, there's a window size. It's in the TCP header, and it says, hey, I can receive this much data. This is how much buffer space I have. So if it starts to fill up, it can be a problem. But we're good, right? Data's coming in pretty steadily as we ramp up the connection. It sort of has sort of like a wave pattern, but it's going up and to the right. There's always space in the receive buffer available. It's just not as fast as we expect. There's not any, we could look and see if there was any data loss, but when I look at this on the receiving side, like, okay, well, it's going. Yes, it's not going fast enough. I don't see like a bottleneck here. So why don't we go have a look on the sending side? So we have both captures. Close that. Let's see what it looks like from the other end. Open. There it is. So just real quickly, we'll verify. We have 2 connections here. There they are. And we have the Threway handshake. Notice anything different about this one? Let's go here. Did you see an MSS, the same MSS on the other side, maximum segment size? So maximum segment size is only advertised, again, in the Threeway handshake, and that's telling the other end, here's the maximum amount of data that I can receive of TCP payload, right? Not counting the headers, just TCP payload. So what does 8961 probably mean? Well, so this is the per packet, this is the amount of data. So if we look at the other one, it's 1460, which is pretty typical for a 1500 MTU, right? But this one is much bigger. Jumbo frames, right? But we didn't see it on the other end. If you recall, we looked, it was 1448, I think. So something has changed the MSS. Is that a problem? Maybe. But do you think if this is over some sort of 9 milliseconds, some internet connection, some circuit, do you think there's jumbo frames end to end? Maybe there's some overhead somewhere. So something in the middle, usually a router, firewall, or something, will do MSS clamping because it knows what its MTU is going forward, and if it's 1500 or whatever it is, and it sees an MSS of over 8,000 bytes, it's going to go in there and change it and bring it down to the appropriate level so it can go across without fragmentation or being dropped. So probably not a problem, but again, it's just another thing that goes into your little file bank when you're looking at this. So here, remember these 1448 in this column, these are the sending side. The ones with 0 are just the ACKs coming back. So this, if we scroll through this one, give a little more space. It looks different from the other side, right? We don't see the same data ACK behavior. So you have to think about, again, when you're capturing, from which end you're capturing and what it looks like relative to that perspective. So if I'm receiving data and I know that I'm supposed to ACK every other packet, I'm going to ACK as soon as I get 2 packets. If I'm the sending side, I can send X number of packets at a time depending on what my congestion window is. So if you start out in slow start, it might be 2 packets, then 4, then 8. But at some point, you can send, however many packets, 25 packets. Well, if I'm allowed to send them, I'm going to send them all at once. And it takes time for them to go out and to be received, and acknowledgements generated and come back. So here, from this perspective, the sending side, you see many more data packets going out before you see acknowledgement packets. Again, not a problem, it's just perspective. So, okay, fine. Let's go have a look at our graph. At a glance, it looks very similar. Up and to the right, smooth. So let's zoom in. And you can see slow start. And then, pretty quickly, the space between the packets and the receive window goes to almost nothing, right? If they touch, if you can click on the packet and you can go to it in Wireshark. So if we had been scrolling down a little bit longer, we would get to this point and see what? TCP window full. So I'm sending data. The receiver is telling me with every ACK how much receive buffer space it has, so I know I can't send more than that amount of data in one go without an acknowledgement, because I'll fill up the window. So if we look, let's see. So bytes in flight, when we hit TCP window full, is 212.992. That means we've sent that many bytes are in flight and have not been acknowledged. And if you look at the ACK that comes back, its window size, sure enough, is 212.992. So we get an acknowledgement. Great, we got an acknowledgement. Now I can send 2 more packets because each ACK is ACKing 2 packets, right? So now the window's open, 2 packets worth. So I send 2 more and whoops, full again, gotta wait. Now we get 2 ACKs back, which means it's ACKed 4 packets. So I can now send 4 packets before I fill the window again. So I am being throttled by the receive window on the sending side, right? Pretty straightforward. If I were to have looked at this side first, I'd be like, oh, okay, this is a receive window problem on the receiver side, and it was, it may have been the one that had like the lower window scale, so maybe we just need to bump up the window scale. But we looked at the other side, and we did not see its window getting full. It was keeping up. It was acknowledging packets as soon as they came in, right? Every 2 packets, ACK. So that was not, it's not the receiving side's fault. So what we can do is if we click on, well, let's do this. We're going to add a column. And if you want to add a column to Wireshark, the easiest way to do it is just right-click on it and do Apply as Column. So pretty much almost anything down here you can apply and add as a column. And at some point in the past, I had this one, the round trip time to ACK the segment. What that means is I sent a segment. How long did it take the ACK to come back to me? That should be around round trip time in general, right? And our round trip time we know is around 9 milliseconds. As you can see, these ACKs are around 9 milliseconds. That's what we expect to see. But let's sort everything by that. We'll scroll down to the bottom. Well, that's different, right? That's not 9. These are the ACKs coming back, and they're 60, 50, 40, 30, etc. All these milliseconds, way higher than 9. There's also another graph that can be useful to visualize round trip time. It is under the stream graphs, and it is called round trip time. And if you click on the wrong packet like I did, you won't get anything, so switch direction. And here we go. So this is like a dot for every ACK's round trip time, and you would expect to see it clustered around 9, which obviously it is somewhere in that range, but we've got plenty that are way above the round trip time. And if you zoom in, you can see it's just really all over the place. So, we don't have data loss. The sending side is doing everything it can to send data. The receiving side is acting as fast as it can. Remember, the throughput is bound by the ACK rate. I can only send data if it's being acknowledged. At some point, I'll have to stop. So the ACKs need to be coming like clockwork regularly on time to me. If they're delayed, sending is delayed. So if you remember the graph on the other end, how it was kind of spread out like with a butter knife, had that kind of wave instead of, do I still have this one open? This guy, he's sending them out fast, right? Just like a packet train, it's going out. When they come out the other end, they're all spread out. And these acknowledgements are all spread out coming back. So, what do you think could cause something like that? Device in the middle. A big buffer, some shaping, QoS. This is one of those cases where, whoops, it is the network, depending on what your definition of the network is. But we've probably got a deep buffer here, a configuration of a device. So my recommendation, if you take captures on the very edge of your network and you see the behavior, as far as you can to your edges of your responsibility, and you still see this behavior, you know it's in the middle, then you have to go to a provider, or potentially it is in your network. It is some shaping device on the edge that you can then track down. So this absolutely was that type of issue. So unfortunately, this is one of those where it turned out to be the network, but instead of people finger pointing and saying, well, the packets tell you exactly, not pinpoint where yet. That takes additional work to narrow it down to the where, but the what is very clear here that you can take to your team and have a discussion about where to go with that. So, back to here. How are we doing on time? I have what, till 10:30? 10:45? Okay. Again, some of the takeaways that I came up with for this, the basics, the initial round trip time. If you don't know that the round trip time is 9 seconds, then that's what's to be expected for ACKs. Those are things you want to file away. The MSS size, we saw it. The jumbo frames here, not over here. It's not a problem. And the window size, right? That was key in finding this issue, was seeing the window, fill the window on the sending side. And it's important here to think, where you're capturing from and what it should look like. Are you going to see ACKs immediately? Are you going to see ACKs coming later? But thinking about perspective is very helpful and a good exercise. And then, in terms of the application behavior, kind of what you expect to see. If, this is really talking about like iPerf 2, iPerf 3, making sure, you see what you expect. Okay, the next thing is a quick little tutorial on TCP. That is my delightful daughter, who's now 7 and just finished first grade, so that was a long time ago. All right, I hope you took a lot away from that. Don't try to make a video with your kid when she's sleepy and cranky. All right, so the next one is interesting. NFS hang. I had a buddy who actually works in tech support for a company. Said, hey, we've got this Linux server, bare metal, talking in NFS to a NetApp, and it hangs at some point in the connection. They've tested different flavors of Linux, and they don't see the issue, so they're definitely looking at this Linux server, but they're not quite sure what the issue is. When it hangs, they do a quick ping, so they still have IP connectivity, like the whole stack isn't frozen, it seems to be this connection. So let's have a look. So when he sent this to me, I think I am in the, can I make that? I should make that bigger. Right? So this is the directory. And if you look at the NetApp PCAP and the SLES 12 PCAP, one's 1.5 gig and one is almost 1 gig, right? Some people's machines can maybe handle that. It won't completely explode. Mine certainly won't. Even if you can get it to load, it might be very slow. So when I'm given a big PCAP, there's a couple things I like to do. Now there's for me, the definitive topic on this is Jasper's session. I don't know if he's doing it this year, but it's in the retrospective from years past about finding the needle in the haystack. Excellent stuff. So for me, I'm like, okay, I want to take this PCAP and break it down maybe into smaller chunks. And actually, I've done that before, so I'm not going to. And one way to do that is with TCP dump. I'm going to break it into 100 megabyte chunks and give it a new name with -client. Run that. Wait. And now we have multiple files at around 100 meg each. So let's open one of those. And we will open the first one. So that's going to be way easier to work with as a start. But it's not ideal, right? Because I don't know where the problem is. And I've got, 10 or more files to kind of work my way through to figure out what I need to do. So right away, just glancing, I see the TCP length. This appears to be jumbo frames. And if I look at what we've captured, well, we've captured 1,500 bytes. Do I need 1,500 bytes per packet to troubleshoot this? Probably not. I don't know. It is NFS, so if it's an application issue, I'm going to need the NFS, but I'm going to assume that maybe I don't. So what I can do is cut this down a little differently. With edit cap, it comes free with every installation of Wireshark, no extra charge. We're going to cut it down to say like 78 bytes. There's, just real quick. There's Ethernet, there's IP, there's TCP. One of these I thought, VLAN. So we want to, we do like 14 bytes for Ethernet, 4 for the VLAN, 20 for IP, 20 for TCP, and another 20 just for giggles. So take the file. This one is that, and we'll do snap, right? So we'll just take 78 bytes from each one. And that is 128. That's not too bad. So let's open that one. And then we'll have the whole thing. Open you. So it's still not, super swift, but it's usable. Okay, so let's have a look at our conversations. There is one, port 2049. If you're NFS, it rings a bell. We're still loading, okay. All right, three-way handshake. Three-way handshake. Not there. I could search for, TCP flags, send equal 1. I'm not going to find it. So after I finish smashing everything, because I don't have the three-way handshake, I sat back down to have a look. Let's take that off. So I immediately expressed my displeasure to my friend and said, you didn't give me the three-way handshake. He's like, I know, these are long-running connections. It takes a while to get to the hang. He's like, I'll work on it for you. I was like, okay, fine. So it looks like we have jumbo frames. You slide it over. And if we do just a little scroll action to see if we spot any patterns or anything. Now, while it is, file transfers over NFS, it's not, the protocol is not just like, HTTP or FTP or whatever. It's like, give me that, here you go. Take it, right? There's more going on at the protocol level with NFS, so we may not necessarily see our nice, neat little TCP pattern. But, we can see it's definitely going. There's very low latency. This is on a local LAN. So let's just have a quick let's take a shot at the our graph. I'm sorry?
Are you going to have to look at the graphs on each one of the packet captures since you split it up?
No. So this one, I split it up initially. I opened one of them, saw that each packet was 1,500 bytes captured. So I went back to the original file, the gigabyte file, sliced it at 78 bytes per packet, and now I have one file for the whole thing. So this file covers the whole thing, and yeah, we have some interesting action here. So remember, what we're looking for is an up and to the right graph for throughput. And it does that multiple times, but very strange, right? We have it going up and to the right very quickly, dropping way down here, going back up here, dropping down here. So I think this is the first time I've actually seen this in a graph. Does anyone know what's happening here? Somebody what?
Somebody's having a heart attack.
Yeah, and it flatlines, yeah. Yes, yeah, probably so, actually. Well, let's zoom in to the bottom of this little drop, and we'll click on a packet down here at the bottom. Towards the bottom, that's probably close enough. Let's go back. Okay, so our sending side .11, here's the sequence number, right? It's a big number. This is a 32-bit integer, is the sequence number, which has a maximum value, right? So we see it here, 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 and then it rolls over to here. So this is low latency, lots of data being transferred, multi gigabytes. You can only have 32 bits in your sequence number field. So what happens when you get to the highest number you can get to? Starts over. So that's what the graph is showing you. And, I certainly have known that sequence numbers do this, but I don't think I'd seen it in a graph before. So, just for interest's sake, this is, at the bottom, right? We just rolled over, we're at the bottom. So what I'll do is I'll set a time reference on this packet. So now we're setting this packet as time 0. And we're going to go, zoom out, and we're going to go to the top. I better zoom out more. It's a lot of data. And now we'll zoom in on the top. All right, that's close enough. So now we're at the peak, right before it rolls over again. So that is .11. It rolls over right there. So that took, so now this is, my other time column is time since the beginning of capture, or time since your last reference set. Because I set a reference of where it rolled over the first time, and I've gone to where it rolls over to the next time, it took 10.56 seconds to do that. And we know exactly how much data was transferred, right? Because it's 32 bits. So we can just do a quick calculation. So if we do that, that's how many bytes, right? 2 to the 32. And it's, if we care about bits, we'll do it times 8. That's how many bits. If we divide that by 10.56 seconds, that is bits per second. We can make it a little more friendly. There's K, there's M, and here's GB. So about 3 gigabits per second is what we're dealing with here. Okay, so now that we kind of like, whoa, kind of the initial shock of that is worn off, we're like, okay, let me do this. The other thing that sort of I noticed looking at this, look at this TCP length. We know it's jumbo frames, right? We saw we saw at the beginning the TCP length was a typical jumbo frame size for TCP length field. This is 62K in one packet. What is that about? Is that a problem? Not really, but it does make analysis really annoying. So I mentioned offloading earlier about checksums. Well, you can also do TCP MSS as an offload. So TCP can just say, hey, I've got 62K that I need to send. Here you go, network card. Go break it up into MSS-sized chunks and send it out. But because we're capturing between the kernel and the driver, we don't actually see what goes out on the wire. So we see what TCP is handing to the card, which is 62K. This is one reason why, if you can possibly capture with a tap or something not on the box itself, it's very useful, because you can actually see what's on the wire. And here we just kind of have to guess. So, back to our graph. We'll zoom back out. Now we know that the weird peaks and valleys shouldn't be a problem of themselves, but we very then clearly see this long flat spot here at the bottom, where we assume is the hang that we're talking about, that we're looking for. And as I move my mouse around, you can see how it automatically highlights the little circle are the packets. As I move my mouse along, you can see it jump to the next packet. And there's a certain pattern to this space between them that is a hint about what may be going on. So if I click on it, it'll go there. And you see the retransmissions, right? These are the highlighted ones in black and red. And they're sending 8,960 bytes. And the time deltas here, they jump out a little bit, right? We can go to the beginning. So we have a time delta of around 195 milliseconds, right around 200. Then we go to 400. Then we're approaching 800, 1.6, 3.2. What does that sound like? Right, exponential backoff. So I send a packet. I'm sending packets. I start a timer. I expect to receive an acknowledgement of the data that I sent within a certain amount of time. It's different on different operating systems, but here it appears to be around 200 milliseconds. When that timer goes off and I have not yet received the acknowledgement, I've got to resend that packet. That is a retransmission timeout. So that's happening, and from the graph you can see it's happening for a really long time. Right? It appears to maybe recover a bit later, but eventually the thing dies. And in here, when I was looking at these, let me see if I can find a dupe-ack. So if I'm expecting you to send me packet 5 and you send me packet 6, but I never got 5, I'm going to say, oh wait, I'm going to send an acknowledgement for 5. And every single packet I get after that that's not 5, I'm going to remind you that I asked for 5. And those are duplicate acknowledgements. So you can see the ACK number here is consistent on these dupe ACKs. And we're up to 100 and something dupe ACKs for this one sequence number. And if we go down, looking at and this is where having the three-way handshake is really useful, because I would expect to see on, most operating systems, selective acknowledgements. But there are, those are buried in the TCP options on every ACK, if there's duplicate ACKs happening. Well, we're up to 173 duplicate ACKs. I don't have any TCP options. That tells me probably that it wasn't enabled in the three-way handshake, but I don't know, because maybe it got stripped out. Maybe it's not turned on. I don't know, because I don't have the three-way handshake. So I asked him to do that, to get it to me. Do I have... So he ended up doing a span at one point, and he got me, I think, one that says span. It's 191. I won't bring it up. It's terrible because we're talking. This is high throughput. Span on a switch is lower priority. There's tons of drop packets. Which yes.
Why do you see like 4 in a row of those? Are they like absolutely identical packets or retransmitted?
These. So.
Like the timestamps exactly the same as milliseconds.
They're a little different, but it's microseconds. So when I say I'm expecting 5, you give me 6, I send an ACK saying, no, I wanted 5. You send me 7, I send an ACK saying, no, I wanted 5. You send me 8, I say, no. Every single out-of-order packet will generate a duplicate ACK.
So, but there's no two-way conversation there, it's just 4 in a row.
Right, so these ACKs were generated from data received higher up. So, like this is data being sent, but it's not the one I wanted. So every single packet I received, and again, those ACKs are responding to something further up. And again, it's difficult because it's ACKing individual packets, which I don't see. This is 44,000 bytes, which isn't what really went on the wire. That, you divide that by the MSS, that's how many packets actually went out. So the ACKs are, you're receiving ACKs for packets you never actually see in this capture, which is why offloading can be a challenge. He gave me a span capture, which is, quote, what's on the wire, but in this environment, the span capture had tons and tons of drop packets. So they weren't like literally dropped on the network. They're not packet loss. It's the capture process dropped them. So it's really hard to analyze that. Yes?
Kary, how can you tell that the packets were actually missed whenever you're just looking at the capture?
So when you're looking at the capture and it tells you previous segment not seen or whatever, if you don't see like duplicate ACKs or the receiver saying, hey, I missed a packet with a dupe ACK, so you're missing packet 5. You might see an ACK that says I received packet 5. You never saw 5, but you see the acknowledgement say it received it. So you don't go into packet loss mode. You don't do retransmissions and duplicate ACKs. It continues on. Without that, you're missing the packets. So I did get the capture. I verified SAC and timestamps were not in the options for the Threway handshake. So one, I said, you need to turn SAC on. You do have packet loss in your environment. That's what kicked off this whole thing. SAC will help the performance if you enable that to be able to use selective acknowledgements. And TCP timestamps is generally default as well. And then, do you know what they're used for, or one thing they're used for? It's called PAWS, P-A-W-S, protection against wrap sequence numbers. It's exactly what we've got here. Now, is that, if you, basically within a certain time frame, you can have the same sequence number on the wire, or, at least out there, but it's really two different pieces of data, right? Because we wrapped. It's not the same data. So this helps TCP keep track of what's valid and what's not. I don't know if that would come into play here, and honestly, it wasn't the problem, but I said, go back, find out why SAC is turned off, but turn it on, do your test. They did, and the problem went away. They opened a case with the Linux folks, and they said, yeah, it should be on by default, slap your hand for turning it off, but they did acknowledge it was sort of a combination deadlock of the lack of SAC and some sort of TCP kernel issue that they filed. So that was, I don't know who decided to mess around with the options and disable it, but once it was back on, the problem went away. Yeah, how we doing? We're okay. Again, unless you really know what you're doing, I do not recommend changing TCP default settings. There's a lot of things around, I've seen on the internet, people talking about time wait cycles and buckets and changing some of those things. Unless you really understand the implications of what it is you're doing, it's probably best to leave it as it is. And again, I'm having to do my best guess at a lot of this stuff, and maybe I would have seen it way sooner if I'd had the Threway handshake to see what options were missing. And the offloading, right? It can make things difficult, just like you were talking about the acknowledgements. I'm receiving acknowledgements for tons of packets I never actually see on the wire because of offloading. Okay, I want to, one more quick thing here before our last one. If you guys haven't heard about Wireshark, here's a little infomercial for you, I think.
Is it a network problem? Is it an application problem? Do all your SNMP and NetFlow graphs look fine? Are you tired of playing the network blame game? Maybe you've tried finding some lost packets. You've probably even tried swapping the cables. If you've tried everything and still can't find the problem, you need Wireshark. Wireshark lets you look directly at the packets on the wire. No more blame game. You'll save the day and be the hero. The best part? Wireshark is absolutely free. But that's not all. Included with Wireshark is edit cap, merge cap, reorder cap, and many more. When network problems get you down, turn to Wireshark. Wireshark is provided in many languages at no cost to you. Learning to use Wireshark will cost you time, practice, and training. Attendance at SharkFest is highly encouraged. Wireshark is not responsible if you read the packets wrong and tell the server team they have a server problem when it's really your 10-year-old firewall dropping packets.
All right. Hopefully you guys met the star of that video. I think he's here this week, John Ford. At least he's supposed to be here. So. John Ford did not come. No, different John Ford. The guy in the video, he is also John. Yeah, different John Ford. John Ford in this video is supposed to be at the Riverbed booth. Anyway, introduce yourself. Tell him how much you enjoyed his thespian, efforts for Wireshark. All right, last one. This one's interesting. Actually just came up at the Europe SharkFest, and I talked to the guy, and we threw this together real quick for Europe. This is also a pretty interesting one. So blank web page. It's either so slow, it's excruciating, and people just give up, or it just never seems to load, it just spins. It's basically unusable. Telco, well, we're making changes, but nothing will affect a web app. Finger pointing. I'm sure you guys never have to deal with finger pointing when it comes to application performance. And of course, the network team's like, no, our network is clean. No issues there. But a good way to figure out where to actually point the finger? A PCAP. So let's have a look at a PCAP. And this one is called, we'll start, so I have client and server, which again, if you can get it from both, if you can get a capture from both ends, it's fantastic. In terms of where to start, to looking at the data, I like to, if someone is complaining, I want to start from their perspective. What do the packets look like from the side of the connection of the people who are complaining? So this is a client side, and if we have a look at the PCAP that he gave me, it's a web app. So there's multiple TCP connections with a web app. Well, he narrowed it down. He was able to narrow it down to one connection, so I thank him very much for making the job a bit easier than digging through and trying to find the problem. So he believes he's discovered the issue, like in the PCAP, just trying to understand it better. So we have one TCP connection, we have a three-way handshake, and let's come down here and have a look. We've got MSS, window scale, SAC, no timestamps, but and what's missing from this one? Right, have a look at those. And then we'll come down to this one. What's missing from the options? MSS. What happens if there's no MSS? Well, I believe RFC 879 says the default size, 536. Look at this. Is that the problem for a blank web page? Probably not, but right? So that's definitely feedback to go to your who was it, the server? Yeah, the server team. You might want to fix that. Okay, fine. So let's have a look at the round trip time. About 44 milliseconds. Based on this, where is this? We already told you, client side, duh. But, it's between the SYN and the SYNAC. Throughway handshake, and then there's like a 1.2 second delay for the next packet coming from the client. Is that a problem? That's over a second's a long time on the network. Is that a problem? I don't know. At the beginning of a connection for HTTP, well, nothing's going to happen, right, until the client asks for something. So we're waiting on, this is the GET request. Maybe it's user time. Maybe, browsers will start up multiple connections to a server already there to, cut down the round trip time, and then they get used as needed. So maybe the connection was set up, and then, the request didn't come down through this connection until 1.2 seconds later. Client wait time, whatever the client delays on the client side at the beginning of HTTP, I'm not too worried about. But again, then there's 50 milliseconds, which is just barely over round trip time from the server. So that's a pretty quick response. And it is sending data, 536. So we get a response back pretty quick. Okay, we're off and going now. So we'll do our little scroll. And you can see in the little cheater pane on the right, we've got some nasty stuff coming up. We're going to scroll down. And some subtle highlighting jumps out here. This is a rule that I have, and you can, if you want to know why something is highlighted, you can go under the frame header, and you can see the coloring rule. So this is delta time displayed is greater than 190 milliseconds. Sometime in the past, I put this in to maybe help me spot delayed acts or something, and I just left it in. So I find it useful. So you can clearly see we have some delays. And look at these deltas. 300 something, 900 something, 3 seconds, 12 seconds, 48 seconds. Is that the normal backoff that we see? Not that I'm really aware of. If we're talking, the typical backoffs for retransmissions, it's usually doubling. This is doing more than that. But the numbers, if you're, a computer person, network person, packet person, those numbers and the changes between them should definitely tickle the back of your brain, right? Those can't be on accident, those deltas. 3, 9, then 3 seconds, 12 seconds, 48 seconds, right? So let's back up a bit. I mean, these weird retransmissions. So this is why I like to have my sequence numbers right here, really close, ready to go. I remember years ago reading a comment on some website. A guy had pasted some TCP dump output and asked a question about sequence numbers or something, and a guy responded and said, I've been looking at TCP dump output for 15 years, and I've never had to bother with sequence numbers. I'm like, what are you doing? What are you even doing? I mean, okay. I found that interesting, humorous. So let's have a look. We've already talked about sequence numbers today and what they represent. I've got my sequence number of this packet. I've got next sequence number that I expect to see in the next packet that it sends, and the current acknowledgement. So just for example, we'll start here. I'm just going to read off the last few digits. So we have a current sequence number of 0748. We sent 536 bytes, so you add that to get the next sequence number, which is 1284. If we come to the next packet, you come down, it is in fact 1284. Well, we sent another whopping 536 bytes. We expect the next sequence number we get to be 1820, so we come down the next packet. Sure enough, it's 1820. Now we're at 2356 is the next expected sequence number, and this is the first delay. Well, that's right, 2356, 2892, 2892. So it doesn't appear that these are retransmissions or, packet loss. These packets are in order. They're just inexplicably delayed. And if we scroll down more, we see this number getting up to 60 seconds. I mean, if you're talking about a blank page, if you have a delay like this in the transport for HTTP, I mean, you see nothing happening on your browser screen, right? You're just waiting. You're going to get coffee, do whatever. You're frustrated because something's happening in the background. We don't know what. Eventually, we do get a previous segment not captured. So let's see if it really is. The last packet sent, 5036, and the next expected sequence number, 5572. What did we get? 6108. That's not in order. And if you do the math, it's 536 bytes that's missing. So it appears, possibly, we dropped one packet. Could it be a capture problem? Well, let's see. So the data continues on. And remember, the one we're looking for next is 5572. So this data rolls in, and then we start to ACK. And what do we ACK? 5572. Even though we've gotten all these other packets, data continues to come in, and we continue to ACK 5572, saying, okay, you've sent me this data, but I'm missing 5572. Every subsequent packet you send me, I'm going to immediately respond to you with an ACK saying, no, I need 5572. If we go down to the options, so we did have SAC enabled here, you can see it keeps a list, a range of here are the packets I do have. So you don't need to resend these to me. I just need 5572. So eventually, we have these duplicate ACKs. If we keep scrolling down, apparently a ways. There it is. We finally get 5572. So that's just recovery. You say, well, why so many duplicate ACKs, right? How many did we get up to? We got up to like 56 duplicate ACKs. And again, you have to think about perspective. I'm on the receiving side. So these packets that I'm receiving, they were sent, however, I forgot what the round trip, 44 milliseconds, wasn't the round trip time? They were sent 44 milliseconds ago from the sender. He already sent them out the door. They're on their way here. No one can stop them from coming. So I'm going to receive them, even though somewhere in the middle one got dropped. So all those packets that were already out the door, they come into me. I say, duplicate ACK, no, you dropped one, or we dropped one somewhere, 5572. And let me find a good run of these dupe ACKs. And if you look at the SAC block, it starts at 6108, but for every new packet that comes in, it increases the right-hand side. You see the number going up? So these acknowledgements are acknowledging data that has already been received. And we're saying, hey, I've got them, but I still need this one, which we eventually get. Okay, so we've got one bit of packet loss, which honestly, one bit of packet recovery is not necessarily a problem. That might slow down throughput. It's not going to cause a hang. Our real problem is back up here. Even though these are in order, there's huge delays. So let's take the first one that's delayed. I'm going to copy, let's see, TCP sequence. I'm going to copy this as a filter. Copy as filter. Let's go to the sending side and see what it looks like. All right, I got to fix that. Right? Okay, so we can do, what is it? Is it Control F? Find. So I don't want to filter it and only display the one packet. I just want to go right to this packet. So you can use the find and use a display filter, and it will go find that packet that matches it. Here it is, 2356, right? That's our sequence number. That'd be a little cramped. You still read that? All right, here's our delta column. Here's that packet. Here are those ones that were sent. Remember, we received them all in order. So here they are in order. Do you see a delay? There is 1 millisecond delay, but not 300 or 900 or whatever. All these packets left at the same time. Look, there's no delay between these packets going out. Right? So if we come down, start scrolling down, we can see something's coming up. So we're sending, again, we're just sending data. And then we get here, which is a retransmission of 2356. That's the one we're talking about. So retransmission, 295 milliseconds. If we go back up, let me go back to the first one, and I will set a time reference on this guy. I'll go down to the retransmission. Yeah, it's still, no, sorry, 350. So the time since I set that time reference in my first time column over here on the left, 350 milliseconds. That's a nice round timeout number, right? So I'm sending data all day long, And when I send the data, a timer starts, right? If that timer expires without it being acknowledged, I have to resend it. Here, the timer is clearly 350 milliseconds. I never receive the ACK. So I send it again. We come down. Here's the next one. So these packets were never ACKed. They're retransmitted. On the other side, did we see packets show up twice? No, right? They were in order. They were heavily delayed, but they showed up only once. So let's go back to, so what I want to know is, I sent this packet twice, it showed up once. Which one showed up? I go to the first one, and we're actually going to dive into the IP header. IP ID is very useful for finding the same packet in different captures. The IP stack is shared across all TCP connections, right? So this increments for every packet that's sent on any connection. From that way, I mean, if we look at this, if we kind of scroll down, 3508, 09, 10, 11, 12, all in order. So maybe the server's not doing a lot otherwise. So 3508. We go to the, here's where it showed up. Was there a question? No? Yes? 3744. That's not it. If we go back to the server side, we go find the second one. It is 30, there it is. The retransmission showed up on the other side. And if we start looking at the deltas between these retransmissions, it might start to look pretty similar, right? So let's test the next one. Let's see, is it 28? Yeah, 2892, 31153. We come over here, 31153. So we received the retransmissions. We did not receive the first time it was sent, right? We can tell that with the IP ID. That's how we know. Now, the ones that were coming in, 3506, these are the packets that were coming in before the delay started. 505, 506, 507, we would expect this to be 508. It's not. The 508 one never showed up. Poof. So these are the later retransmissions. The last one that we have here was 507. If we go down to after the delays stop and the packets start coming in again, now we're at like 607, 608. And remember, these I lost my, yeah. So what we're seeing here, if we go back and look at these guys, we have packets coming in. Everything's fine. Then everything freezes. One pops up later. Another one pops up later. They're all in order. There's huge delays. But our IP IDs are moving like this. The ones that show up have an IP ID way further down. And when the data string picks back up, it's the original packets that were up here from before the retransmissions were sent. Does that make sense? Let me go back to this guy. So before the retransmission started, we're sending data. And for about, 5 or 6 packets, these all disappeared. And then these packets, we got the retransmissions through, and all the packets that were sent in the meantime start popping up. They start coming in, the original ones. So this is, 6644, remember, this one is sent before the retransmissions, right? This is when everything is fine. We haven't retransmitted yet. So this is sequence number 6644 with 607 as a IP ID. And do I have 66? Oh, this is it. 6. This is it. So this is the exact packet. So what's happening is we're sending data, it stops. Then we get retransmissions somehow poke their way through. And that somehow what frees up a log jam somewhere, and all the original packets that have been held up this entire time come rushing in. That is not normal. If you see behavior like this, where packets get held up, retransmissions somehow magically get through, sometimes it'll be the third or the fourth retransmission will finally poke through, and then these packets just come out of nowhere that have been held up somewhere, that is not normal. And the times I've seen this, it's always been some kind of application packet inspection engine. It needs to get all the HTTP data to do security scans, to do whatever policies you want to do on it. And if there's any kind of problem with it, things freeze, and then it just blows up, and either packets come through or the connection gives up and dies. In this case, while it seems to recover some, it continues to have problems. Eventually, there's still a minute delay here. Eventually, the server just gives up. It's like, what? We can't seem to get on the same page here. We give up. So you take this data and you capture from both ends. You capture at the edges of your responsibility, so you know that it's not you in your environment that's doing this. Again, this is not normal behavior. And you take the data, you go back to the telco who said that, we made some changes, but it's not the network. You say, yes, it is. Here's the data. This is not normal behavior. Sure enough, they had a network probe doing packet inspection, it had a bug, patched the bug, problem went away. So finger pointing can be put to an end for that. So I think we're about out of time here. Know the basics, IP ID. It's very important to be able to try to match packets, be able to do some basic sequence number analysis so you know where we are in the order of the flow. If you have it from both ends, that is fantastic. That's what really helped us here. If I had just been looking at the client side, I said, you got packet loss, you got something, but I know much better what's happening when I can see it from both ends. When you have the data, you lean on whoever's responsible. I've been on many customer calls in the past, my years doing this, where it's this problem and people are upset. I go, okay, walk you through the analysis with the packets, and everyone, what can they say? Maybe I'm wrong, but we can all agree that, hey, let's go in this direction next. Let's go and figure out the next step. It really kind of shuts down all the finger pointing. And Hondo here is the person who sent this in. That's it. Questions? Packets are fun, right? Hey.
What was the reason for the 312? So you said it was not quite exponential.
Yeah. So that, we'd have to go back. It was either a weird timeout behavior on the sending TCP stack. Do these numbers match up roughly? I think they kind of do. Or it was the probe itself that's causing the problem. It's hanging on to these packets, and then some of the retransmissions are getting through. So it's either the probe doing it, or we could go back and take a closer look at the sending side. It could be the TCP stack on the sending side. Oh, I think I must have done this around Halloween before. I don't know if anyone's ever seen David S. Pumpkins, but anyway. I'll be here the rest of the day. If you'd like to chat about packets or anything I've said wasn't clear, we do try to move at a quick pace. I'm happy to talk with you. If you have packets you want to look at, please do fill out your survey on the app. You can reach me if you have case studies. Please reach out to me here. I used to have Twitter on here, but I kind of gave up on Twitter just as a personal decision. But yeah, you can reach out to me here. I'll be happy to talk to you about packets. Enjoy the rest of your day.